Okay, hi girls. Yeah, so I thought let me give you today free, just so there's no urgency for us to do an extra lesson now. So let's just cool it a bit. I don't want to overwork you. All right, so I'm a bit of umming and ahhing whether to do this with you, but I thought I'm going to quickly discuss this with you, and then as I go, I'll explain why. So this is conservative forces versus non-conservative forces. This is technically not in the IAB SAGS document, okay? And you won't get the equation in the data sheet. You can use it. It's not like you're not allowed to use this in the IAB, but there are always other ways that you can work it out. And it can be a bit confusing. So I'm going to just quickly go through it. If you don't like it, you can ignore it, okay? Like I said, there's always another way to work something out, okay, with this. So the conservative force, what you get is it's a force acting in a closed path. So there's no other forces acting on it, and where the work net is equal to 0. So like the example we did the other day where the friction and the force, so we had, remember we had a frictional force and an applied force, and they were equal because the acceleration was 0. So if you had an applied force, and they had to be equal because the velocity was 0, because the acceleration the velocity was constant, but the acceleration was 0. So that made the net work 0 joules, because friction was removing energy from the system and the applied force was giving it, but they were giving the same amount of energy. So that's this where you would use conservative force. All kinetic energy is converted into potential energy and then back again. So this is your up and down motion. We're looking even up and down a slope, for example, up and down steps. So total mechanical energy is conserved. So it's still using the conservation of mechanical energy. EP plus the EK is equal to the same throughout the whole thing. Now this is important here. It's independent of the path you take. So whether we are going up a slope, like we did with that one question, if we need to get from A to B or B to A, if we are going down the slope to get down to this, or if we're going down like that, it is independent of the path. We lose the same amount of potential energy. Okay, so that is what independent of path means. Don't worry about the little noises you hear. My nephews are here, so Ryan likes to hum. Okay, so we got force down, motion up, we got the 180. Basically what we're saying is there's the mechanical energy, the EK plus the EP at the top is equal to the EK plus the EP at the bottom. Or it doesn't have to be top and bottom, it can be in position 1 and position 2. Okay, so that's that. Non-conservative forces. Now this is where it gets different to what you're used to. So it's a force acting on an object where the work net does not equal 0. Okay, so this is really for nearly all of your other things. The total energy of the system is still conserved, but the mechanical energy is not. So you've lost energy with something. So your total energy is still the same, but your kinetic energy could have been converted into heat if there was friction, for example. The most common non-conservative force is friction here, and it is path dependent. Okay, so, and that would be friction. If you go up there's 2 slopes, okay, and you have the same height, and path 1 is rough and path 2 is smooth, the friction will affect us more on this path than on this path, but you're going up the same height. So this is where we're looking at a force that then is path dependent, because we know friction does this. It depends what you slide something on will affect your friction. Okay, so for example, we've got friction and applied forces. So a ball rolling up the path, you've got friction coming down, and you've got a ball rolling down the path, you've got friction going up. Now this is the formula for non-conservative forces. You can see it's a W with an NC, standing for non-conservative. So it's the work done on something like friction. And what they do is they say, well, there's a change in kinetic energy and there's a change in potential energy. And if you add those changes together, you'll get the work done for the non-conservative force. But like I said, you don't ever have to use this formula. There is always another way to work this out. Okay, so I'm a bit reluctant with you even knowing about it, but I don't want you to be caught unawares if you do see it in a memo, for example. So like there will always be another way, okay, especially because this is not mentioned in the SAGS document and you don't get the formula on your data sheet, okay? So please don't worry about this if I've confused you with this. All right, just ignore it then. Okay, so we're going to look at power. This is our last for mechanics. Then our mechanics is done, so we're going to look at power. So the definition of power is the rate. We love that word rate because we know we're going to have time. The rate at which work is done, or the rate at which energy is transferred. Remember, work done is equal to energy transferred. So the unit of power is the watt. Capital letter W because it's after a person's name. And your work is in joules and your time is in seconds. So here we can see again another unit for power would be joules per second. Okay, and so here's an example. Remember, you do have power in electricity, and it's very similar to this as well. So they can interlink these. The energy of a 300 kilogram dragster exerts an average force of 53,000 newtons over the first 20 meters of its race. The dragster takes 0.8 seconds to cover the first 20 meters. Calculate the work done. Okay, so we know work done is equal to the force times the displacement or the distance that it was pulled. Notice that I gave you 300 kilograms. So that 300 kilograms means nothing here because our motion is horizontal and the force that the weight will give it is up and down, is on there. So if you had to draw a free body diagram of all the forces, this would be your weight, and it has nothing to do with anything. You've got the force of the engine pulling it forward, and they never even said anything about friction because we're not even looking at it, because what they want is the work done by the engine. So, and the engine exerts this force, okay? The engine exerts this force and they want of the engine. So you're not working W net here. So it will be 53,000 times the 20 meters. Okay, and that works out to be 53,000 times 20. 106, 1, 2, 3, 1, 2, 3, 4. 4 zeros and joules. Okay, for B, it says what is the power? So we know power is equal to the work over the time. And we've got this as our work. And our time is 0.8 seconds. So the power that the engine is exerting, and this is where they work out power of engines and stuff. So they can see how powerful any engine is by doing this type of calculation. Obviously, it's a bit more involved in engineering. 1325000 watts. Make sure it's a capital letter W for power. Okay, a power lifter is able to lift a large weight through a vertical height of 1.5 meters in 3 seconds. Okay, the weightlifter applies an average upward force, so his force is also going up, so that's cool. We don't need to worry about the cos theta. I didn't worry about the cos theta here either because it was the same direction. So the force is equal to 27,000, and it says calculate the power output of the weightlifter. So an output is what he is putting in to lifting this. The output is now the power exerted onto that weight in order for it to lift up. Okay, so we know that we're working with power. Power is equal to work over time. So we don't have our work yet. So we have to work out the work again. I'm not going to worry about the cos theta here because they're in the same direction. So 7,000 times 1.5 meters. This guy is very tall. I suppose he can lift it up past his head. Times 1.5. Okay, so we got 50 joules. Okay, now we put that in there. 4050 divided by the time is 3 seconds. 3, and the power that came out, because remember he's going to have power from his muscles, and that's the input, is that power, using up the energy from your muscles, and the output is now what is the result of all this power being put in, is that the weight gets lifted up. Okay, this power, you'll be using Faraday's constant here. And this is on your data sheet. Sorry, what am I talking about? Thinking of Faraday's constant. Faraday's constant is a small f. Sorry, ignore that. So this is working at average power. So if a force causes an object to move at a constant velocity, I have exclamation mark here, okay? Because if your velocity is changing, you can't work out the power. Yeah, this isn't a change in V. This is a constant V. So a locomotive engine with a mass 20,000 kilograms, which has an output power of 1,750 kilowatts. So imagine the amount of fuel it's burning, for example, that would be your input, and what is it giving to the train? That's the output. Remember, always change kilos to the other unit by putting 3 zeros instead of the K. Pulls the carriage of total mass 40,000 kilograms at maximum speed of 55 meters per second along a straight level track. Calculate the magnitude of the forward force. Okay, so what do we have here? We've got power and we've got velocity, so we can use this formula. So we can go P is equal to that, so we've got 175,000 is equal to the force times 55. That is our velocity. So our force becomes 175,000 divided by 55, which gives me 3181,82 newtons. Okay. Now it says the engine is switched off and the brakes are now applied. Calculate the power of the braking system if the train is brought to rest in 3,64 seconds over a distance of that. Okay, so we're looking for the power of the braking system. Now here we have a change of velocity, so we can't use this one. So we have to use the other one. So we're going to use, I'm just going to do it over here. So we are going to use this one. Remember, we can't use this. There's a change of velocity, so we're not going to use that one. So what are we looking at? So we know the initial velocity. Remember, we can work out our work here by working out our energy. So our change in kinetic energy is equal to a half v final minus v initial, so it's minus 55, okay, because we are losing energy. So it would be 0,5 times if the train, now remember, we've got to consider the whole mass of the train. So we've got the locomotive engine and one of the carriages. So we have to include that into our calculation. So that is then going to be 60,000, am I right? Yeah, 1, 2, 3 times negative 55. Okay, so we get an energy change or energy loss of 1,65 and 4 zeros. Sorry, don't know why I put that. 165, 1, 2, 3, 4. Okay, now they never gave us any indication of any other force being applied, because if the brakes have been applied, and they actually did say that the engine has been switched off. So the only force that is applied to this is the braking system. We're going to ignore friction because they never said anything about friction. Okay, so we are going to consider that as our loss of energy. So work done is equal to the loss or gain of energy. So we know it was a loss, so I'm not going to worry about putting a sign in here. So this is how much energy we lost over 36.4 seconds. And so the power exerted by the braking system was 165.0000 divided by 36.4. Okay, 45329.67 watts. All right, so that is the power. The last thing I'm going to look at is power efficiency. Now, if you make an engine or you make a generator or anything that is using power or giving power to something, remember it's all about the energy conversion. So if you are putting in a lot of power, and like let's say I run a generator, but I use a whole bottle of petrol in 1 hour. Okay, so all it gives me is 1 hour of electricity for a generator. That might not be efficient, because a more efficient generator would take 1 liter or 1 bottle of petrol and convert it into 5 hours of electricity. Okay, so that would be more efficient. So you want the power. Remember, fuel is a potential energy and it can be converted into kinetic. So whatever power you're putting in divided by the power that is coming out, you want it as close as possible to 100%. Efficiency is percentage. Sorry, I didn't put the thing there, so it must be a percent. That's why we're timesing by 100. So power in divided by power out divided by power in divided by I don't know what I'm saying. Power out divided by power in times 100 is going to give you your percentage efficiency. And if you are producing something you want, or using something, you want it as efficient as possible, because you don't want to waste energy. Okay, so that's also looking at things like solar power, all of that stuff. You don't want to waste the energy. Okay, so I hope that makes sense. Please ask me questions if it's not, and you can start the think tanks. I think this is carrying on tomorrow, on Friday, if I remember correctly. So I'm not going to see you tomorrow. I don't see you on a Thursday, so we're not losing any time. Okay, so I'll see you on Friday. So you can then work through that on Friday. I'm sure I've put it for you to carry on Friday. All right, my girls, love you lots.